Hello, students. This is the review for Unit 2 of Geometry B, the second semester of your geometry course. And as usual, I'm going to remind you to have your notebooks handy for the vocabulary that you may or may not already have in there, but you will need for the unit test. This unit is on area and volume, and we started out by talking about the area of polygons. Polygons literally means many sides, and a polygon is a flat surface, a two-dimensional surface. So in general, the area of quadrilaterals, which is a four-sided polygon, is the base times the perpendicular height. Okay, why do I say perpendicular height? Because we think of a quadrilateral as a square or a rectangle, and they already have 90-degree sides, but not all quadrilaterals do. A parallelogram can have any type of angles. So if you can create a height which is perpendicular to the base and multiply those two lengths, then you will find the area of a quadrilateral. For a rectangle and a square, that means the area equals length times width, or it could be written as base times height. Same thing. A rhombus, which you remember has sides that are equal to each other, but not necessarily with 90-degree angles. The area equals half the product of the diagonals. So I've got one down here. You can see that this is a rhombus because there's 3 tick marks on each side, meaning they're all even or all equal. And I've shown the diagonals written. Now, these diagonals are not necessarily equal to each other. You can remember if this was squished down almost flat, one of these would be short, one would be very long, but they always bisect each other. So they divide each other in half exactly. And if you know the lengths of those diagonals, which you can find out because it divides the rhombus into triangles, then you can multiply them together to find the area of the rhombus. A trapezoid is another quadrilateral. And remember the formula, because there's 2 bases on a trapezoid. Let me just draw one out here. Let me see if I have one. No, but I have some lines here. Okay, so a trapezoid might look like a quadrilateral with parallel sides that are not necessarily equal in length. So because there are 2 bases, you have to take the average of those 2 bases and multiply it by the perpendicular height. So the height would be somewhere, whoopsie, let's see. The height would be somewhere like this. That would hit the one base or both bases in a perpendicular way. And then you would add the lengths of these 2 bases together and divide by 2. That's just another way of taking the average. So if you think about it, it makes sense, because if this were a square or something, you could take one side off and sort of piece it together. You're basically looking for the average width times the actual height. Now, we talked a lot about surface area in here, and that seems to give students a big problem. But remember, it's just a matter of finding the area of all the different sides of a 3-dimensional figure. So a base of a shape or a 3-dimensional shape, such as this prism up here in the corner, consists of a polygon, a quadrilateral. It's 2-dimensional. Now, another vocabulary word that you learned was lateral area, and that is all the surfaces that are not the bases. So in this prism up here in the upper right, the bottom is considered a base, so the top of its identical sides would also be considered the base. The other 4 sides going around the perimeter would be considered the lateral sides, and those have an area which added up would be the lateral area. The total area, or the surface area, would include the area of the 2 bases. Trapezoids, as I was trying to explain before and trying to draw, is the area is found by multiplying the height times the average of the bases. So in this one, I would add 15 plus 9, which would give me 24. The average of those would be 12. And if I knew the height of this, well, actually, I can calculate this base, I think. So let's take a look at this. This is a 45-degree angle right here, and since it forms a right angle here, I know that this angle is also 45. And look over here on this other side, I have the exact same thing. So if I draw here at 90 degrees, I've got something called an isosceles trapezoid. This side over here is equal to this side over here. We're not given the length of that side, but we could figure it out because this is a, let's see if we can figure this out. If these two sides are equal to each other over here, since these are congruent triangles, then we can take 9 from 15 because this area right here is a rectangle and the side below it's going to be the exact same length as the length above. If I subtract 9 from this, I get 6. That means this side will be 3, and this side will be 3. And I can use the Pythagorean theorem to figure out, do I have enough information? Yes. So I know the height is also 3 because a 45-45 triangle is also an isosceles right triangle. So the height is 3. And the average of the bases we already figured out was 9 plus 15 divided by 2, or 12. So the area of this trapezoid would be 36 square units. It doesn't say what units it is. So we'll put units squared. Okay? So again, the formula is the average of the bases you find by adding the top base and the bottom base and dividing by 2. In this case, it turned out to be 12, and using the information that we were given that this was an isosceles trapezoid gave us a lot of hints because we knew that the sides were equal to each other. We could calculate the length of those sides by taking the 9 out of that 15, and the leftover length of the bottom base was split into 2 equal pieces, each 3, meaning the height was 3 because a 45-45 triangle is also isosceles. And that gave us all the information we needed to find the area of this trapezoid. Pyramids play an important part in this unit. You learned a lot of new terms and a lot of different ways to calculate the slant height, the lateral area, the surface area, the area of the bases, etc. So here, the slant height is the height of one of these lateral sides. Notice that a pyramid always has triangular sides, but it is the length down the side. And if I had to draw it in here on this triangle that's already been drawn, it's the hypotenuse of this right triangle that's drawn inside the pyramid, extending from the apex up here to the midpoint of one side, right down there. Now that's an important measurement because it helps us to find the length, if it's not given, of any particular pyramid. Then you can use the Pythagorean theorem. Now, usually in the Pythagorean theorem, you think I have to have 2 sides to find the third, a squared being one of the legs, b the square of the other leg, and c the square of the hypotenuse. We know that this hypotenuse is going to be the slant height, and we don't have the length of this side down here. But one thing we do know about a pyramid is that the height is calculated to the very center. That means that we can split the side length, which is 10, and that is going to make that triangle have a leg of 5. So using that, I've got 5 squared, that's one leg squared, plus 12 squared, the other leg of this triangle, equals the slant height squared. We'll call it C for now. 5 squared is 25. 12 squared is 144. If I add them together, I get 9, 6, 1. 169 equals c squared. If I have a squared variable on one side, the only way that I can find the actual value is to take the square root of both sides. The square root of c squared is simply c, and the square root of 169 is 13. So I know that the slant height of this particular triangle, or this particular pyramid, is 13 units. Now, looking at these triangular sides, you can use the regular triangle formula to find the area of the sides, which is 1/2 the base times the height. Now, we didn't know the height, but now that we figured out the slant height is 13, that's going to be the same for each one of these triangular bases. We know that the base is 10, the height is 13. If I multiply them together, I get 130. And by definition, the area is 1/2 of that. So if I divide that in half, I end up with 65. So 65 square units take up the area of one of these triangular sides. Now, if I am asked to find the lateral area, that is all 4 triangular sides of this pyramid, but not the base. Since I know there are 4 of them, I can simply multiply 65 by 4 and get 260 square units for the lateral area. If I want to find the area of the base, and this one appears to be square, I can multiply 10 times 10, that's 100. And if I add that area to the lateral area, I will have the complete surface area, which in this case is 360 square units. So just from 2 little measurements being given, we were able to calculate the lateral area, the complete surface area, the area of each lateral side, and the slant height of this pyramid. Now, we also learned that we can do a lot with triangles. We can put them inside other polygons, we can put them inside circles. And remember, the formula for the area, the general formula, is 1/2 base times height. Now, there are some special triangles that really allowed us to do a lot of things, very powerful formulas. There are relationships between the sides and all 3 sides of a 45, 45, 90 triangle. So in that last problem, or in the trapezoid problem, we realized that we had an isosceles right triangle. That tells us a lot. Because 2 of the angles are equal, 2 of the legs are also equal to each other. In fact, the ratio of them is 1 to 1. Those are the 2 sides. And then the hypotenuse is that number times the square root of 2. Now, because that's the ratio, if you know the length of any one side, you can find the others. For instance, if one of the legs is 3, you know the other leg is 3, and the hypotenuse would be 3 times the square root of 2, because that's the way ratios work. Okay, we also learned about 30, 60, 90 triangles. These are very important, and they show up inside hexagons and circles. We use them all the time. Those sides also have ratios. The ratio is 1. That's the shortest side. The second shortest side is the square root of 3, and the hypotenuse is 2. That means there's always one side that is half the length of the hypotenuse. And I'll show you an example of one of these in a minute. An equilateral triangle is exactly what it says, equilateral, all sides are the same. So the lengths of all the sides are congruent, don't need any ratio for that. And there's a special formula for the area of an equilateral triangle that is going to come in very handy. If you don't already have it in your notes, write down that the area of an equilateral triangle is 1/4 times the side squared times the square root of 3. And you can imagine that this was taken from this ratio of the 30, 60, 90 triangle side lengths. Now, where can we use these? Well, hexagons are very special polygons. They create 6 equilateral triangles inside them. So if I drew all of the diagonals on a hexagon, it would divide the whole thing up into 6 equilateral triangles. It would go something like this. And if I split any one of these triangles in two, as I've done here in blue, you can see that it splits one side, making a right triangle. And because each of the angles inside an equilateral triangle is 60 degrees, 1/3 of the total of 180, I know that this half angle here is 30, and the larger angle here is 60, because it was an original angle of the 36 of the equilateral triangle. Now, another word that was introduced to you is apothem. The apothem is the length of the line segment from the center of a regular polygon perpendicular to the side. So in this case, we know that the side lengths of the hexagon are 8. They're all the same. This is a regular hexagon, by the way. Because we know that it divides the hexagon can be divided into equilateral triangles, we know that these radii, if you can call them that, are also equal to 8. That means we know the measurement of half of a side would be 4. And since we know the short side is 4, the long side of each of these 30, 60, 90 triangles is 8, then we know, according to our ratio for 30, 60, 90 triangles, that the longer side, or in this case, the apothem, is 4 times the square root of 3 because of the ratio that we've already learned about 30, 60, 90 triangles. Now, where does that come in handy? Well, if you had a hexagon that was inscribed in a circle, you could draw out this hexagon completely, get the angles that you need, and the apothem would approximate the area of that triangle within the circle. And we're going to use that a little bit later. Now, in circles, we learned some new words. The circle, we know that general formula for the area is pi r squared. What is pi? It is simply a constant. It's approximately 3.14, but it is an irrational number and goes on forever. There are people that have memorized it out to hundreds of decimals. And the radius is squared and multiplied by 3.14. This relationship exists between every radius of every circle and its area. It also relates the circumference of the circle. Pi is used in that as well. This is a very important constant and allows us to find many, many different measurements. Now, the area of a sector, which is a pie-shaped portion of the circle. So if I just pretend this is a pie and cut it into pieces, 6 pieces, for instance, each one of those sections would be 1/6 of the pie or 1/6 of the circle. And you could calculate the area by dividing it by the size of the sector. Now, segments, on the other hand, and these are easy to get confused, is this little leftover section once you inscribe a triangle within the circle that has the same angles and dimensions as the sector. That little leftover section is called a segment, and you spent a lot of time in your lessons trying to figure out the area of those. Now, a cross section can be taken of any shape, and what I've shown down here is a cross section that was taken of a sphere. You can see it's like some kind of sheet metal came straight across and just cut right across the three-dimensional figure. What it does is it creates a flat surface, and that flat surface is some kind of polygon, or in this case, a circular figure. These can sometimes be hard to imagine, but if you draw it out, you should be able to figure this out. Now, what would be the area of the cross-section of this sphere? Well, it depends on the length, how far away it is, but we're only given one measurement, this 4-inch radius. But we know that the 4 inches extends to the end of this cross section on both sides. And if we knew the angle, we could actually find the length of the diameter of this cross section. Let me draw that in for you. And calculate the area of that circular shape. So with just a little bit of information, you could calculate the area of that cross section of the sphere. Okay, we learned a lot about the areas of cylinders, cones, and spheres. Again, the base formula is area equals pi r squared. The radius is always a super important measurement. Remember, if you're given the diameter instead of the radius is just half of it. So you have the information you need. Now, looking at a cylinder, the lateral area, if you can imagine it, let's say that this was a can of soup, and you cut the label off the can of soup and unrolled it and laid it out on a piece of paper or on a surface. The shape of that label would actually be a rectangle, right? And it would have the same height as your cylinder. It would just be wide enough to wrap all the way around. So this side of it would be the same as the height of the cylinder, measure h. And if you imagine this unwrapping, the length of this is the circumference of the top of the cylinder. And we have formulas that show us how to calculate that. And so we actually have both measurements to figure out the lateral area of a cylinder. Now, this one says that the radius is 4. I happen to know that a circumference is 2 times the radius times pi. That means it's 2 times 4, or 8 pi. If that's 8 pi, then this length of the label is 8 pi. The height is measured as 6, and so the area is 6 times 8 pi, or 48 pi. Now remember, when you're working with pi, you don't always have to approximate the value. It's more accurate to leave it in terms of pi, meaning that your answer will still have pi in it. If you have to simplify it in another way, your lesson will tell you, or your question will tell you, what to use for the approximation, such as 3.14. Now, taking a look at the cone, you can do some similar applications. The lateral area is pi times the radius times this cursive L, which is the slant height. How would we find the slant height of this cylinder? Well, I've drawn in a little internal triangle, and because I've drawn it so that it's perpendicular to the base, I know that this is a right triangle, and I can use the Pythagorean theorem to find the slant height. Remember, that's a squared plus b squared equals c squared, and I'm again looking for c. So 11 squared plus 5 squared is going to equal the hypotenuse squared, which in this case is the slant height. 11 squared is 121, and if I add that to 25, I end up with 146. 146 is not a perfect square, so I'm simply going to put square root 146 over here. And to find the lateral area, it will be 5 pi times the square root of 146. Okay, now we also learned the formulas for spheres, and even though we didn't work with them a lot, you need to be able to calculate this with the information that you have. For the surface area, oh, I think that this bullet is supposed to be under here. To find the surface area of a cone, I would just simply add the lateral area that I just found to the area of the base. What's the area of the base? Well, that's going to take us back to the original area formula, which is pi r squared. And I see that the radius here is 5. So that will equal 25 pi. So the whole surface area would be 5 pi times, square root 146 plus 25 pi. Now we get to the sphere. The sphere's area, surface area, uses the formula 4 pi r squared. And I'm given the radius is 3, so I can rewrite this as 4 pi 3 squared. 3 squared is 9, and 9 times 4 is 36. So 36 pi is the surface area of this sphere. In general, the volume of a figure is the area of the base times the height. Now, I don't mean the base one side, I mean the area of the rectangular base. So if you could see through the middle of this prism, you could see that there is a rectangular base down here that matches the base on top. And if you can calculate the area of that base, in this case 4 times 2 would be 8, and then multiply it by the height, then the volume would be 24 cubic units. Now, that's in general, and it certainly applies to a prism. Remember that the area of the base will be length times width, and when the B in a formula is capitalized, that means the area of the whole base, the polygon base. The volume of a cylinder is given as pi r squared times h. A cylinder has a volume of 175 cubic units and a height of 7. What is the diameter? Okay, so we need to work backwards with this type of problem. So we have the volume. So I'll replace V with 175 equals pi. We do not have the radius. In fact, they're asking for the diameter, so we don't know what that is. But we do know that the height is 7. So I just want to undo these sides and solve for r squared. So I'm going to divide 175 by 7. It's not going to go in evenly, but let's go as far as we can. 14 would leave me, oh, it does go in evenly, would leave me with 335. So 7 times 25 is 175. So now I have 25 equals pi r squared. Now at this point, I could do a couple of different things. I could divide 25 by pi, and this one doesn't tell me what to use. So if I had to divide 25 by, say, 3.14, hang on while I grab my calculator. I usually have it right here, but my screen is being taken up by something else. So 25 divided by 3.14 gives me 7.96. Approximately, and that's going to equal r squared. Now, in order to find r, which I had to find in order to find d, I'm going to have to take the square root of 796. So I'm going to hit my little square root marker, if I have it on here, and looks like I don't on this calculator. Yes, I do. Let's see, square root. equals, okay, 7.96 square root Sorry, this is taking so long. I usually use a different calculator. Okay, we're going to have to estimate. Well, the square root of 9 is 3, and the square root of 4 is 2. So it's going to be closer to 9. So let's say that this is going to be about 2.75 or so. And because that's the radius, I would have to double that to find the diameter. 2.75 times 2 would be 5.5. So that's an approximate answer, and that used the important steps that you would need to calculate that. If the additional measurements were given to you, you wouldn't have to go that route, but you should always be able to work backwards like that. Now, we talked a little bit about the cross-section of a sphere, but any three-dimensional shape can have a plane passing through it, and you should be able to imagine what that shape might look like. So if a plane, including points A, B, and C, cuts through the cube, this cube, what is the shape of the resulting cross-section? Well, if it went straight through at a 90-degree angle, then it would be a square, but this one appears to be slanted. So you can see that some sides would be a little longer than the others, and it's going to come out as a parallelogram. Volume of pyramids, cones, and spheres follow these formulas. The volume of a pyramid is 1/3 of the area of the base, that's that capital B, times the height. So it's exactly the same as a prism, except it's only 1/3 the volume. So here we have our square base of 100 square units, and we have a height of 12. If I multiply those together, I get 120. And if I take 1/3 of that, then the volume would be 40 cubic units. A cone uses a very similar formula. In fact, it's identical, but the base here is going to be a circle. So pi times 5 squared would be 25 pi, is the area of the base. And if I multiply that by 11, I get 275 pi. And if I take 1/3 of that, I get 91.6 repeating pi. The sphere has a volume of 4/3 pi r cubed. Notice that we popped up to cubed because this is a three-dimensional figure. The other ones, we were using the radius for only finding the base. That was a two-dimensional figure. So if 3 is the radius, 3 cubed is 3 times 3 is 9 times 3 again is 27. So 27 times 4/3 times pi. And I can simplify this. 4 times 9 is 36, so 36 pi is the volume of this sphere. Now, we talked a little bit about similarity. Remember way back when we talked about congruence, similarity is like that, where all the angles of two different polygons are the same, but the size will be proportional, but not necessarily the same. Two similar polygons have areas of 16 square inches and 64 inches. Okay, let's draw it out. We don't know what the shape is, but it says they're similar. And these are both perfect squares, so I'm just going to imagine that they might be squares. There's a small one and a much larger one. Okay. The ratio of the pair of corresponding sides is 1:2. So whatever the length of this side is, say it's, well, we know it's going to be 4, then this one would be 8. If the ratio of the lengths of the sides is 1 to 2, then the ratio of the area of the figures is 1 to 2 squared, or 1 to 4. Let's check that out. 16 times 4 is indeed 64. So that's true. If the ratio of the lengths of the sides is 1 to 2, then the ratio of the volume of the shapes is 1 to 2 to the 2 cubed, or 1 to 8. So if you were talking about a prism where you had doubled the sides, double the length of every side, you now know what the volume of the resulting shape would be. It would be 8 times the volume of the previous one. So you might think, well, I doubled everything, the volume would be double as well. But just like we can see here, the area is not doubled simply because we doubled the length of the sides. It actually goes up by a ratio of 2 squared. And for the volume, it goes up by a ratio of 2 cubed. Okay, now we talked a little bit about rotations, but for some reason, maybe because we're not 3D viewers, we can't always imagine what these are. This question is on your test. It says, what three-dimensional shape is formed when the right triangle ABC, which I've drawn, rotated 360 degrees about its side AB? So try to imagine that this shape is being rotated, and it's important which direction it's being rotated. So if it turns around side, AB, I think this is actually the instructions say AB, but I think it's supposed to be AC because the illustration shows AC. So let's assume that it is being rotated around AC, which means it would be coming just as far over to this side as it did to the other side. And it would be coming forward that far. And I'm going to try to kind of draw this out so that you can imagine it. And it would be going backwards that far as well. So it's going to be spinning around in a sort of a circle on the base. In fact, you can assume that when something is rotated, there's going to be a circle somewhere in this illustration. And right here, I'm going to try to draw this, and we'll see how this comes out. There's going to be a circular base here. And if you can imagine the sides at every step extending out an equal measure all the way around this circle, then you can gradually see that this shape is going to turn out to be a cone. So it's spinning around, so just kind of maybe a blurry look around is going to leave all these side spaces coming out to create this cone-shaped figure. So remember, when a two-dimensional figure is rotated, it's going to create a three-dimensional figure. And in this case, it would be a cone. Okay, and I think that that's just about all I have for you in this presentation. Let's see if I can grab one more slide. Nope, it looks like that's the end. So with that, I will sign off. Now, you may feel like you're still confused about something that I discussed in this presentation, or that you had other questions that you came upon during this unit that were not answered by the presentation. If you don't feel prepared to take the test, just give me a call at the end of this unit or at the end of this lesson, which you know you have to get credit for this assignment anyway. And let me know if you would like to meet and discuss some of these things or some other things that you had questions about. Or if you had any questions on here, you're welcome to go back and watch them again. Either way, let me know what kind of help you need, and good luck on the test.